Hello, fellow problem solvers. So today we're going to be doing a problem from the 2021 United States Junior Math Olympiad, problem number 1. I suggest you try this problem out for a minimum of 40 minutes, ideally an hour and a half to 2 hours, but not more than 3.5 hours. If, on the other hand, you'd like to go along with us, I suggest you take 20 to 30 minutes and put your first ideas out on paper, play with the problem, figure stuff out. And the reason I'm really inviting you to do this for this problem is because it's a beautiful, nice problem if you're into the sort of combinatorial algebraic thinking. The only thing you really need to know is what does it mean for f to be a function. So now, let's begin. So this is the problem. Find all functions which satisfy these two things. Now, when you first see a problem, what do? The answer is play around with the problem. So here, let's just plug in some values. Say, here, let's call this 1 and this 2. Plug a equals 1 in 2. And what you get from there is f of 1 is f of 1 squared. And because this isn't 0, we can divide by f of 1. And what we get is 1 is equal to f of 1. Yay, we have a value. Okay, now we can plug that in here. A equals b equals 1 into 1, and we get that f of 2 is equal to 1. Okay, cool. Let's just plug in 1. We have f of a squared plus 1, if we just plug in b is 1, is equal to f of a. Another cool thing, this is also, okay, we know this. What else? Well, for me, let me just try to figure out some other numbers. So for me, a big picture view right now is, after playing around a bit more, say, a is equal to b is equal, a is 1 and b is 2, I get f of 5 is equal to 1. And if I plug in, I get from a equals 1, b equals 5, I get f of 26 is also equal to 1. But also if I plug in a equals 5 in 2, I get that f of 25 is now equal to 1. And now if I plug in 3 and 4 here, I'll get that f of 3 squared plus b, 3 squared plus 4 squared, which is 25. F of 25 is equal to f of 3 times f of 4. This is equal to 1. And this, that implies that f of 3 is equal to f of 4 is equal to 1. Now with this in mind, I invite you to play around some more, like we found f of 1, 2, 3, 4, 5 are all 1. I invite you to play around some more with the problem and see, is there anything you notice, any ideas, any hunches that you're getting based on this playing around? And I invite you to pause for 10 to 20 minutes and try to see what your hunches are, and maybe play around even more, try to figure out some more values, try to prove your hunches. So the hunch I have here is that the only answer really is f of x is equal to 1 for all x, and the whole idea of the problem is to figure out how are we going to get every single x. And now, if you haven't had this hunch, I still invite you to play around with the problem for another 10 to 15 minutes, and even if you have, I still invite you to play a bit more. So now I'm going to look at what's the big picture idea. I have some playing around. Okay, let's maybe play around a bit more and then go back to the big picture. That seems something I would do, really. So if I have x, I have x squared, I have x to the power of 4, I have x to the power of 2 to the power of n for every n greater than or equal to 1. That's a natural number. Woohoo! And what I mean by this arrow is that if f of x is 1, then f of x squared, x to the 4th, x to the 2n, they're all equal to 1. But it also goes the other way. If f of x squared is 1, say for some square, then the opposite is also true. Then we'll get this is 1 is equal to f of x. So both cases are true. You can go from squares to their square roots and from x's to their squares. And now the second thing that I'm looking at here particularly is if I plug in a equals b, what I get is that f of a squared is equal to f of 2a squared. And now for here, what I'm thinking is if I plug in 2, I'll get that f of 2 squared, okay, this is 1, is equal to f of 8. So f of 8 is also 1. And then I look, I have 14, I can get 16. And if I plug in 4 here, I'll get f of 4 squared is equal to 1. And this is f of 4 squared times 2, which is 16, which is f of 32. So I have f of 16 is 1, f of 8, f of 32. And I'm thinking, wait a second, I can probably get every single power of 2. So if I plug in a is equal to to the n, then what I'll get is this squared is going to be equal to f of 2 times 2 to the 2n, which is going to be equal to f of 2 to the 2n plus 1 on one hand. On the other hand, this thing right here is equal to f of 2 to the 2n. And now purely inductively, we would know that f of 2 to the k is equal to 1 for every k greater than or equal to 1. Okay, so we're having some more progress. Now from here, my personal next hypothesis was, let me write 2 to the alpha as a squared plus b squared. But maybe for every a, there's an alpha and a b such that this is true, so then I'll be done. And here is the point where it's good to know some number theory. I mean, this is a number theory problem, I'm assuming at least, is that, wait, if a is say an odd number, then b must be an odd number as well. But then this is congruent to 1 plus 1 mod 8, which means it won't be equal to 2 to the alpha. So, and if a is an even 2 to the l times m, and b is equal to 2 to the k times n, then what we'll have is alpha minus the minimum of these, say l is greater than or equal to k. So alpha minus k, 2 to the alpha minus k is going to be equal to m times l minus k, actually minus 2k minus 2k minus 2k squared plus n squared, where n is not divisible by 2, and then this is just false. And this is one idea you might have gone through and then realized, hey, this isn't working. So now I would invite you maybe to pause for another 10 to 15 minutes and play around, find some more ideas. Maybe even take a big picture view and ask yourself, wait a second, what is this problem telling me? What is this problem here all about? And please, I would invite you to pause now. And here's what it is telling me. On one hand, it's like we're moving from x's to squares. Like that's what this part is telling me. If I have an x, I can go to a square, and if I have a square, I can go to an x. This part is telling me if I have an x, I can go to its square times 2. And probably if I have its square times 2, I can go back to the x. And by half, I mean that this is 1. But then there's also something bigger going on here. If a number can be written as a sum of two squares in two different ways, say this is also like c squared plus d squared is equal to a squared plus b squared. And if I have c and d, I can also be done. So there's something about sums of squares that I need to be looking at here. Can numbers be written as sums of squares in many ways? Maybe that's a way I can connect these numbers together, because it's, for example, a 7 isn't that easy. We have like f of 7 squared is f of 49. And what am I going to do with 49? Well, f of 7 squared plus 1 squared is 50. Maybe this can be connected to, this is f of 7 times f of 1 is 1. So f of 7 is f of 50. Now there's maybe a way to connect these together. I don't know. I mean, this is equal to 2 times 25. Maybe there's yes, this is f of 2 times 5 squared. So this is f of 5 times f of 5. And now, okay, now we have it. Now this is 1. Now we get to a 7. But it's complicated. Though maybe it's not too complicated for you. Anyways, here's the point again. After maybe telling you this, that would invite you to take another 10 to 15 minutes and still try to solve the problem. Because really there's so many ways you can solve this that I would really want you to try to solve it on your own way. And here's my next step. So here's what happens when you play around. F of 1 I got directly, f of 2 I got here. F of 3 I got because f of 3 times f of 4 is f of 5 squared. And that's the same as f of 1 times f of 2 squared. And that's how I got f of 3 and 4. F of 5 I got because it can be written as 1 squared plus 2 squared. F of 6 I got in a similar way here. F of 6 times f of 8 is f of 1 times f of 3 squared. That's 1, so that's how I got f of 6 and f of 8. F of 7 I got because f of 7 times f of 1 is f of 5 times f of 5 is 1. So I'm getting many of these numbers I'm getting because they are, one of the numbers that I'm getting is a, and I'm getting it because a squared plus b squared is c squared plus d squared for some c and d that I already have. Or even if not this, I mean in these cases it's not this, it's c squared plus d squared squared. And that's why I'm getting some of these numbers, where c and d are much smaller than a and b. And then I was at f of 8 I had, f of 9 I just got directly, and then f of 10 I already have, and now I'm at f11. And I can't get it as easily. I was getting f11 times f60 because I was looking at Pythagorean triples. I was looking at a squared plus b squared is c squared, and then c might be something nice, so I can maybe deal with this easier. However, that was not the case here, given 61 is a prime. So what I did was I made a huge list of what happens when this is, say, a and b, and this is what's a squared plus b squared. And then I was looking at, okay, can I get 11 as 11 squared plus something squared is equal to c squared plus d squared? And I wrote this out, and I got, okay, for 11 I have 130. That's 11 squared plus 3 squared is 130, and that's the same as 7 squared plus 9 squared. So now I had f of 11. And this now I got because a squared plus b squared was equal to c squared plus d squared, where a was the number I needed, and c and d were smaller numbers. Now with 12, I did a similar thing, like I just filled this up. I got 145 matching here. And so I had f of 12 times f of 1 is equal to f of 145 is f of 8 times f of 9. And this is 1. Now f of 13 I could be done with writing it as 3 squared plus 2 squared. But I decided to look at it in this same table to see if there's a pattern, a more general pattern I could use. And I got it as f of 11 times f of 7. And then f of 14 I could write in two ways. I filled it up. I was filling it up to make sure that I could write it in two ways so that I do not miss any particular pattern while I'm doing this. And now from here, there's a couple of ideas. One idea you could follow is looking at this sort of representation, looking at, okay, let me try Pythagorean triples. What do I have with them? Another one is really playing around with more cases, writing F15, 16, 17, 18, 19, 20, and figure out if you see any sort of pattern once you're making this table. And now with this play, I go to my next step, which is, so I have f of 1, f2, all through f14 is equal to 1. Now, one approach to solve this is to think, okay, maybe inductively. Let's say I'm looking for, I have all the numbers less than n. Can I find n? How do I find what's f of n? And one way is to make n squared plus a squared equal b squared plus c squared for some a, b, c. I mean, and this means n squared minus b squared is c squared minus a squared, just to make things easier, more, because I can then divide this into two factors. So now let's try a couple of b's. One is, say, b is n minus 1. So then I'll have this side equal to 2n minus 1. Yes, 2n minus 1 is c squared minus a squared. Now if 2n minus 1, if it had this is c minus a times c plus a, does this have any factors? Okay, there might be cases here, but let's try to do something much more concrete, something that's much more general. Let's do b is n minus 2, just playing around. And then I'll have n squared minus b squared will be equal to what? This will be 2 times 2n minus 2, which is 4n minus 1. Now if I write this as c minus a, and this as c plus a, what do we get? Let's see. So we have c minus a is 4, c plus a is n minus 1, and now I get 2c is n plus 3, c is n plus 3 over 2. Okay, so if n is odd, I have an identity I can use. And I'll get also a is going to be equal to this minus this over 2, n minus 5 over 2. So I'll have this identity if n was odd. Then I'll know that n squared minus n minus 2 squared is equal to what? So we have, where was it? Okay, n plus 3 over 2 squared minus n minus 5 over 2 squared. So what this tells me is if we're using some induction, if n is odd, I will be done. And this here is exploring the idea of just how to solve this directly, immediately. Now for n evens, we can look at, okay, say n is 2k, then I have 4k squared. And now can I use, let's see, why can't we use something similar? Say n minus 3. N squared minus n minus 3 squared, this will be 3 times 2n minus 3. Yeah, I think I'm correct with this. And if this is c minus a, and this is c plus a, c minus a. Oh, now if I add them up, I'll get n and then minus 3. So 2n minus 3 needs to have some factors for me to be able to be done with this. So now this is interesting. Now, is there a way to work with this perhaps? Say if 2n minus 3 is prime, then we can't really break this up. There's only one way to write this. And what if I write it as n squared minus n minus 5 squared? This is 5 times 2n minus 5. If this number is prime again, I can look at it as n squared minus n minus 7. Say n minus 1 squared. It's going to be 1 times 2n minus 1. Now, if this isn't prime, I mean, they can't, all three of them can't be prime because they're different modulo 3. But if this is some a times b, then I can write, okay, let's use x times y. Then I can write this as c minus a is x, c plus a is y greater than or equal to x. And then what we'll have is c is going to be equal to what's x plus y over 2. Oh, and we know these two numbers are odd because they're 2n minus 1 is their product. And a will be y minus x over 2. So both of these will be normal numbers, so we can actually do this like this. Not a bad job. I'll be honest with you, I just got this idea now. I didn't think this was going to go anywhere. I was just exploring this problem. But it seems like we can finish it like this? Question mark? If this is now x times y, I can write a plus c is 5x, a minus c is y, then I'll get a is 5x plus y over 2, and we just need to check that a isn't equal to n, where xy is 2n minus 1 over 5. This is so weird. This could actually work. There might be a couple of edge cases and whatnot, but this actually could be a solution. Okay, this wasn't my plan, but it seems like we have a viable solution. I would still need to think about this. But now let's move on to a different set of ideas that you could have used to solve this problem. So another way to look at this problem is to think about Pythagorean triples, because you have this, and if this is some c squared, then that's f of c squared by this. So maybe it's interesting to look at numbers of the form where a squared plus b squared is c squared. And if you know Pythagorean triples, you'll know all numbers of this form that are integers are of the form m squared minus n squared, 2mn, and m squared plus n squared times some k. But let's first look at the most simple case and see if we can do anything with that. So what do we have when we make a is equal to m minus n squared, b is equal to 2mn? We'll get f of a, f of b is equal to f of m squared plus n squared squared, which is going to be equal to f of m squared plus n squared squared outside. And now this is going to be equal to f of m times f of n and everything squared. And now this we can use to finish the problem, because this is f of m squared minus n squared, 2mn is equal to f of m, f of n squared. Say we already have that odds case finished up, and now we're looking for the evens case. We just say if the number we need is 2k, if we have all the numbers still 2k, then we just set m is equal to k, n is equal to 1, and we get f of k squared minus 1, f of 2k is f of k, f of 1. And by the inductive hypothesis, this thing right here is going to be equal to 1. And if you want to do, you can also do the odds case from here. If you want 2k plus 1, you can just make m is equal to k plus 1, n is equal to k, and then you'll get k, because the difference of these squares is 2k plus 1, and then you'll get f of 2k plus 1, f of k plus 1 times k times 2 is f of k plus 1 squared. This is 1 by the inductive hypothesis, and you're done. Now this is one way of looking at the problem and solving it, thinking about, okay, this reminds me, maybe I can play around with Pythagorean triples because of this condition right here. Maybe I can get something different. And I also got it when playing around. So that motivates me to look at, is there anything interesting if I plug in some Pythagorean triplets? And there is, the problem gets solved. And now the final way is, say you played with these numbers and figured out constructions for n 1 through 25, and you try to notice a pattern. And there actually does exist a pattern, and there's many ways to motivate it. One way is to say, you played around with these numbers and you saw it. Another way to motivate it is, okay, so what you need is, you need a squared plus b squared is c squared plus d squared, where c and d are some smaller things you already have, and you need a and b. Similar idea as before, though here we look at how are we going to represent this number n that we're looking at. N is going to be of some form. If we're going to have a couple of cases, it's going to be of the form m times t plus r, where we are representing n as the form of m times t, and we're going r0 through m minus 1. And now a way to think about this is to say, what would be a nice m? Because, okay, when I have this n squared, I'll have m squared t squared plus something something. And I'll have some other two numbers, cm and dm, squared times t squared times t squared, and I'll add them up. So is there a nice way to get rid of this m? That's the motivation roughly. And the idea is, let's look at n as 5k plus r. Then I'll have this squared on one side, and I'll have 3k plus rc squared, this is say ra, plus 4k plus rd squared, and I'll have something extra for b squared. And if we go through this, what happens is we have 10k ra plus ra squared plus b squared. This is going to be, ra is going to be element of 0 to 4. And the 25k squared cancels out. We have 2 times k times 3 times rc. So we have 2. So that's 6k rc plus 8k rd plus rc squared plus rd squared. And now the question is, can we solve this for every single ra from 0 to 4? Here I would invite you to pause for 10 to 20 minutes and try to solve this for ra 0 through 4. And here's the solution. So what you get when solving these is this. You get this identity for 5k. For 5k plus 1 you get this identity. For 5k plus 2 you get this one. For 5k plus 3 you get this identity, and for 5k plus 4 you get this identity. And now if we have enough base cases, every single one of these will be greater than every single one of these, and we will be able to finish by our inductive hypothesis. And now with this in mind, let's move on to the maybe final sort of way you could have thought about this is, say you had you can have x. X is a number you can get. And if you have x, you can get x squared. So what else can you get? You can get x to the power x squared plus 1 if you get x and 1. You can get 2x squared. Now you can apply these operations again. And you can go backwards with these operations as well. And you can get more of these combinations. You can look at, okay, what if I squared this? What if I apply this in 1? I'll get this number. If I do this, I'll get this number. And you can maybe look at, how could you go backwards? So you could go backwards if you had one of these numbers that can be written as a sum of two squares. So you can go ahead and just like test out different hypotheses. Like while you're exploring, you could be testing out, can this one be written as a sum of two squares? No. Can this one? Yes, but we would just get x squared in 1. Can this one? Yes, but we would just get x squared again. Could this one be written as a sum of two squares? And the answer is actually yes. And the way it could be written as a sum of two squares is the following way. This is x minus 1 squared plus 2x squared. This is using the identity that a plus 1 squared is a minus 1 squared plus 4a. And now with this, you know that you can, from x, you can get to x squared plus 1 squared. And from here, you can get to sort of numbers, what is this? X squared minus 1 and 2x. So now it's a matter of checking this out. So if we have f of x is 1, then we know that f of x squared is 1. But what we also know is that f of x squared plus 1 is f of x, f of 1, and this is also 1. And then we know if we square this, we'll get f of x squared plus 1 squared is 1, but this is equal to f of x squared minus 1 squared plus 2x squared. And now this is f of x squared minus 1, f of 2x. So now we know if f of x is 1, then f of 2x must be equal to 1. And now we have our jump from evens to odds. And with that, we can figure out a different jump from, x to 2x plus 1. And such a jump exists, or we can use our other odds idea. And this is just me showing you many different ideas that you could have come up with for this problem. You explore the problem, and then you figure out an idea from that exploration. But the idea that you pick and figure out really depends on your style. And now, with all of this thrown at you, I invite you to take 20 minutes to 40 minutes and try to write up a solution based on one or more of these ideas, or a combination of these ideas. Here's my solution write-up. So we first say notice f of 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are all 1. And then from here we say, assume there exists a natural number such that f of n isn't equal to 1. And let n0 be the smallest such natural number. By what we found above, we know that, n0 is greater than 10. And from here, we can break it down into two cases. Namely, case 1, n0 is odd. And from here, what we do is, we do this change. And then what we have is that because f of n is equal to 1 for all n less than n0, and because n0 is greater than 10, we have that both of these are 1. So this forces f of n0 to be equal to 1, which means that n0 isn't odd. And now we move on to 3 more cases, namely cases where n0 is 0, 1, and 2 modulo 3. And now here we deal with these cases individually, namely, and we get these solutions. Now all of these are integers and 1, except in this case t has to be greater than 5. So we're left with dealing with one more case, i.e. case 5, n0 is 15, and here we are done because f of 9 times f of 12 is equal to f of 9 squared plus 12 squared, which is f of 15 squared, which is equal to f of 15 squared. And because this is 1, that implies that f of 15 is 1, i.e. for every single n0, we have that this f of n0 is 1. So there is no smallest n0. And now from here, we are done. And as always, thanks for problem solving.